Okay, so good morning to everybody. So today we are going to talk about the geomorphic methods for identification and characterization of active faults, geomorphic markers of tectonic deformation. So these are the books which you can follow, like Tectonic Geomorphology by Douglas W. Burbank and Plate Tectonics, How It Works. So these are the books, and there are other more books. But Tectonic Geomorphology is a good book if you want to go into more detail. So we will be discussing the geomorphic markers, faults, what is the difference between a fault and an active fault, and then establishing timing in the landscape, dating methods, right? These are the things which we are going to cover. So first of all, we can see that Indian plate has moved from south towards north, and it has traveled a distance of roughly 6,000 kilometers. And we can see that the movement basically is like 180 millimeter per year, and this rate has changed. So currently it's around 4 to 5 centimeters per year. And just to because we are in Chandigarh and we are very close to Himalayas, so one very important boundary basically, and we have this 2,500-kilometer Himalayan arc. And we are this Indian plate is basically colliding with the Eurasian plate, and there is a northward movement of 4 to 5 centimeter per year. So this is a bigger concern because we have a lot of population in this area, and we have a lot of active faults and earthquakes. So there is a need to understand that how these things will work out in future, because we have a lot of dams also in Himachal. So just a very, there are many definitions of active faults. There are papers discussing different things, but we are just going to use the simple definition. If there is an activity, if there is an earthquake, let's say, if we put in a simple terms within the Holocene, then maybe we can call it as an active fault. Okay, so that is roughly like, if in within, let's say, last 10,000 years, there is a earthquake, along a fault, then we can call it as an active fault. Then, in Pleistocene times, we can call it as a potentially active, and then in pre-Pleistocene, we can call it as an inactive. So this thing we have to keep in mind. So a lot of figure basically shows a lot of earthquakes, in the Himalaya. These are epicenters. So, very close to Chandigarh, Kangra, and there were these major earthquakes very close to us. There was in 1905 the Kangra earthquake, and the magnitude was like roughly 7.8. And there are other bigger earthquakes along this region. So that is again a motivation to understand earthquakes and active faults. So this is just a diagram showing that the major thrust in the Himalayan belt are basically dipping towards north. And most of our work, which we have done uh, in this area, basically is concentrated along Himalayan frontal thrust, which is very close to this. You can see the Shivaliks, so very close to Shivaliks. We have worked basically in this part, in the frontal part, mostly. So if we are compressing, let's say, if we are now compressing this Himalayan, so any fault can be activated anytime, you know. So that is, and then, maybe there is one fault is activated, maybe two are activated, or, it can be a combination of these things. So Chandigarh lies in seismic zone 4. So this is just a simple diagram showing the different type of faults. So we can have normal fault, strike slip fault, or a reverse fault. So very, uh, very. So can we say that whether this is an active fault or not? How can we say that? Yes. So if there is a movement, but how do we know when this movement happened? You know, how can we quantify that? That this is an active fault, because we are using a kind of a definition of the earthquake happened in the last, let's say. Yes. Yeah. But yeah. But how do you know that's an active fault? That's the question. Dating. So what do you want to date basically? So simply you can think of that. Let's say there is a river which is coming and it is bringing some sediments, and these sediments are deposited along any fault, right? So these sediments are deposited in layers. If the sediment age is from, let's say, 0 to 10,000 or 12,000, you know, and if those sediments are displaced, that means these are, Holocene or quaternary sediments, Holocene. So if those sediments are displaced, then we are able to say, yes, this is an active fault. So we need these quaternary sediments which are deposited on top of a fault boundary, and if these sediments are displaced, and then we date those sediments, and then we can quantify, yes, this displacement happened in the Holocene. Then we can call it as an active fault. Otherwise, we can simply say that's in fault. Okay. So now we are going to discuss basically the tectonic geomorphology. Uh, so because plates are moving, we are having this elevation. And because of this elevation, there is always a competition between the topography and the erosion. And in order to understand what's going on, basically we can have some geomorphic markers. So geomorphic markers, what are geomorphic markers? These are landscape features such as marine or fluvial terraces that can be used to track deformation. Prior to deformation, the surface of these markers represent planar or linear features with a known geometry that can be predictably tracked across the landscape. So yes, we will discuss a little bit more about these geomorphic markers in the coming slides. So techniques and some of the insights gained from them. In many ways, this greatly improved understanding of modern deformation that we now can take the largest strides in interpreting the past deformation and landscape evolution. So uh, basically, we are in Chandigarh right now, right? And we know that we don't have floods in Chandigarh. You know. So you can think about it, that why don't we have floods in Chandigarh? But very close to Chandigarh, for example, in Ropar, where we have IIT Ropar, there we have floods, you know. So the question comes to our mind, what is the geomorphology, or how the geomorphology of Chandigarh has evolved, or how this landscape has evolved through time, that why we don't have floods in Chandigarh? So that is a very, interesting question you can ask yourself as a, student of geology. So we will also discuss, how this landscape has evolved through time. So now if we see the this diagram, uh, basically on the x-axis we have time, and then we are going from fully interglacial to fully glacial periods. So during Holocene, you can see that we are mostly in the interglacial period, right? So it is important to understand that if and the second scale, we are seeing one full cycle, one full climate cycle, because and then in the third diagram, basically we are looking at there at a scale of 1 million. We have many fully interglacial and fully glacial periods. So why this diagram is important? Because when we are dealing with sediments, we need to understand what is the age of those sediments. If let's say that we have some river terrace, and I will discuss also river terrace, how they're formed. But right now we can just think that a river brought some sediments and those were deposited. If the age of those sediment is, let's say, it varies from 0 to 5,000, when we study climate or can we study, that climatic variation in those sediments? If the yes or no? No. Why we cannot study the climatic variation? Because the sediment has only seen the climate of only fully interglacial. It has not seen the complete cycle. So that means those sediments are only deposited during the erosional processes which happen during the fully interglacial period, right? So because we have these, river terraces of different ages. So yes, you can have a deposition because of, a lot of rainfall is happening, or it may be just land is uplifted. So always these two components, whether it is a tectonic or whether it's just a climate. Climate is like a rainfall. You have more rainfall, you have more erosion, and then you have position. So this thing is very important to keep in mind when we are looking at sediments. So if let's say there is a, deposition, some sediments are there, you find in Himalayas, let's say, and the age varies from, let's say, uh, 0 to, let's say, 1 million. That means now these sediments are deposited during various glacial and interglacial periods. So now those sediments can have different climatic zones. If you date them, you can do those kind of interpretation because those sediments are older now. So I think that is clear. Yeah. Okay. So now in Holocene, we can see that we are always in the fully interglacial period. That means we have an advantage. We have an advantage in Holocene. What is that advantage? That if we are in Holocene sediments, we are not seeing the climate cycle. So if we have any kind of deformation, that means that is maybe if the sediments are displaced, that is because of a deformation. So at Holocene timescales, we are confined to a post-glacial era in which the climatic conditions have varied relatively little. You know. So we are not, at a time scale of 100,000 or more, complete or multiple glacial interglacial cycles have occurred. At Holocene timescales, cause and effect can be examined rather directly. For example, if faulting causes the land surface to tilt in a given direction, the timing and the rate of diversion of the river in response to that tilt can be measured. So now, what are the strong imprints on the landslide? What are these drivers basically? What are these major drivers which are driving this tectonic geomorphology or, So these are basically the large scale changes are sea level. If the sea level changes, then the size of the glaciers and the discharge of the river. So these are the main drivers, that generate the different type of geomorphic markers. So these are the main drivers. For example, if you see the Himalayan terrain, you can see the sediments are present along the rivers. So those sediments can be, brought by the river. But sometimes we see the villages are on the top of the mountain where the river cannot flow. So those sediments maybe are of glacial origin. So if you think in terms of like, okay, from where these sediments are coming, either they are glacial, they are glacially generated, or broadly we can say they are fluvial, right? So if there is a village on the top of a mountain, close of the mountain, maybe the glacier was present there and it did erosion and everything. Now the maybe the glacier has melted, but the soil is there preserved on the top of the mountain where the village is situated, right? So these are, very roughly we can divide, okay, the glaciers might have generated those soils and the discharge of. So now the question is like at a time scale of a millions year of more, then numerous climate cycles have created that time average landscape, right? So sometimes we can have three disadvantages which we have in Holocene. The rate of tectonic processes may vary significantly slow or occurrence of deformational events such as earthquake may be sufficiently rare that tectonic signal is obscure. Second, the rate of geomorphic processes that Holocene interglacial times may not be very representative of a long-term rate. So these are the because we are in Holocene, so we might calculate some rate, but that may not be a representative rate of the bigger time scale. The time it takes for a geomorphic system to respond to a change imposed by tectonic forcing can longer can be longer than the Holocene. You know, maybe there is some kind of a tectonic event or something, but the response we see in sediments, maybe it will take more time than the Holocene to occur. So these are some disadvantages. Because the geomorphic system may be in a state of transition with respect to tectonic perturbations imposed upon it. So the present rate of crustal deformation can be compared against the sediment load of the rivers. So these are common example is like the river terraces are almost untouched by erosion and can function as pristine recorders of Holocene deformation. The strength of Holocene studies is that the record is often most complete, the dating is most precise, the rates of many competing processes can be directly measured, and the interaction can be examined. So there are some models which landscape development models which are proposed by different scientists. So first one is the Davis model. Basically, Davis proposed in during 1800s and 1900s that he gave the concept of youth, maturity, and old age. So the tectonic forcing is a impulsive phenomenon that occurs at the beginning of the geomorphic cycle. All of the building of the topography occurs at the start of the cycle. So in this case, we can see that this tectonic forcing or the uplift is basically happening in the beginning, and then slowly and slowly there is a decline, and so the landscape basically evolves from youth, maturity, and old age. Today in the afternoon, we are also going to do the practical, which in this, something like that we can discuss. Okay. So the first thing is that in Davis model, the rock is uplifted instantaneously. And then you have this, slowly and slowly this tectonic forcing is eroded by these different processes, erosional processes. And another scientist, he gave another different idea. He said that, okay, the tectonic forcing is not just instantaneously. Slowly and slowly, you are building the topography. As it is being built up, it is also being, cut down by the erosional forces. So there is waxing and waning, and in this model, it's like a wave, like a pattern of tectonic forcing through time. So that's the second model. Geomorphic processes were conceived as attacking the uplifting region through the period of mountain building, so that the result of landscape could be interpreted as a product of this competition between deformation and erosion. As the rate of mountain building waned, erosion was proposed to overtake deformation rates, thereby causing a gradual reduction in the residual topography. There is another model, basically landscape development model proposed by Hag, who suggested that the rate of deformation and the rate of erosion are sustained for long time intervals. The landscape will come to a sort of balance or dynamic equilibrium. So he proposed a different, so given the finite strength of the rock, Hag realized that topography cannot increase without limit, even if the rates of tectonic forcing persisted for very long periods. In this is different than you know Davis model. That in Davis model you have instantaneous tectonic forcing, but in this case the relief is built slowly and slowly, and then basically there is a equilibrium, dynamic equilibrium between topography and erosion. So as the topography grew and grew, the relief on the hill slope would create forces exceeding the rock strength, and they would collapse. Right? If we just keep on increasing the elevation of the rocks. So at some time, because of gravitational forces, the rocks will collapse. So those will that will cause basically landslides. With continued uplift of the bedrock, additional slow failures could limit the height and the topography would attain. Eventually, the topography would enter into a roughly steady state or a dynamic equilibrium. Consequently, in this model, rate of mountain building and rate of erosion would come into a long-term balance. So if we think that the if the dynamic equilibrium means that the rate of uplift and the rate of erosion is more or less same. So in that case, we can say it's a dynamic equilibrium. Unlike the models of Davis and Planck, there is no need for rate of deformation to become negligible or even to wane at all. That is basically in the Hack model. So uh, in our area, in this Himalayan zone, we can now see that, let's say this is a drainage basin. And if there are different tributaries which are joining the main trunk. And if there is a, let's say there is a fault, you know, let's say there is a fault in front of this, like a, let's say normal fault or something. So if there is a fault right here, this main trunk, it will know, yes, there is a drop of elevation, right? But this one and other tributaries which are behind in this drainage basin, those will not see the change that there is a drop of elevation. So the erosion will start happening first here, and then it will propagate. First, it will come to this point, and then this small stream will understand, okay, there is some drop. Now the erosion will start happening here. And like that, it will progress through the drainage basin. So the channel that crosses the fault sees the displacement first, right? The local base level will have fallen abruptly, causing the river gradient to steepen locally and erosion of the channel to intensify. At this point, all other positions in the catchment will have been undisturbed by the faulting event. So the faulting elicits no initial geomorphic response. So the point is why we are discussing this, that there is a time lag. There is a time lag between tectonic forcing and sediment response. This is an important concept. We need to understand that there is a time lag. So the time lag between the tectonic forcing and sediment response is variable. So Cui and Binot in 1996 developed a model that predicts a lag between the onset of deformation and the response of a geomorphic system to the deformation. So in this, we can see this is we have a tectonic influx right here, you know, and it took some time to erode this, tectonic or impulsive system, and the sediment influx had the maximum peak somewhere here. So there is a time lag, between the tectonic this thing and the response. The overall response of the geomorphic system and the magnitude of the lag depends strongly on the nature of tectonic forcing. If the forcing is impulsive, like as we discussed in the Davis model, then the topography is rapidly created, degrades through time. In tank model, if the deformation increases to a maximum through the time and then wanes, topography gradually builds in the phase of progressively increasing rate of erosion. The maximum topographic expression occurs slightly after the rate of deformation begins to wane because the rock uplift still outpaces the rate of erosion. So again, we can see that there is, a lag between these. In the hack model, if we can see that as the change in the rate of surrounding forcing would push the system towards a new equilibrium, whereas cessation of deformation would return the system to almost Lewisian state in which the topography is systematically degraded. So finally, in the later half of the cycle, the topography wanes despite gradually diminishing rates of erosion. If the tectonic forcing is continuously sustained, then Hui and Binot model predicts that after an initial interval of building of topography, the rates of rock uplift and erosion will become balanced, and the topography will maintain a persistent dynamic equilibrium. This is just an image just to show that we can use uh, lidar, and in this case we are able to see a fault in active fault and also glaciated sculptural topography. So the question is, yes. So question: can enhanced erosion drive up uplift of a mountain summit? So let's say if there is a mountain and we are doing erosion, right? There is a lot of rainfall in Himalayas and the rivers are bringing sediments. So can this cause the mountain to rise above? Yes. Okay. Yes. So yes. So we will discuss that, and yes, the answer is yes. And so we can think of a ice cube basically floating in water. So 10% of the iceberg is basically above the water level and 90% below, right? And if we start taking that ice from above, because of buoyancy forces, the iceberg will rise up. Same thing happens in the mountains. So, for example, this is the ice cube, and this is the original height of the summits. And let's say we have eroded in between, mass. So now, because of this isostatic compensation, you know, the the relief is increased, and we can see that the change in the summit height. So we can see the change is there, and the change in the mean height also, because change mean height was below that. Now it is up. Point. Okay, I can just. हाँ, तो ठीक है. ओके, मैं ठीक है. नहीं, नहीं, okay. So in paleosismological studies, what we do is study of basically past earthquakes, and we want to understand what is the reoccurrence interval. So paleosismology, yes. So for example, like this, So let's say in this case, what we are looking at is basically the trace of the fault, and on the y-axis we have amount of displacement. So we can think of it as like let's say there is a fault and there is an earthquake along this fault. So it ruptured in the similar manner. So earthquake 1, earthquake 2, and earthquake 3, they're rupturing in a similar manner and a repeated magnitude of offset at any location. So these we can call it as a characteristic earthquake. But a random earthquake, on the other hand, if we have a fault trace, then earthquake 1 and earthquake 2, the rupture length is different and the location is also varying. So we can call these as random earthquakes. So non-steady state changing relief and non-steady state changing mean elevation in this and steady state topography. So such constraints present some great challenges to researchers in tectonic geomorphology. Morphology. It is inadequate to document any modern rates. The rates for interval throughout a climate cycle or the rates that integrate an entire cycle are needed. This integration requires clever ways to measure quantities of material moved from and added to a landscape. So four attributes of Himalayan Tibetan origin and how they may be linked. So first, the thickening of the crust beneath the Tibetan plateau appears to have caused crustal melting of at least some of the lower crust, which then becomes weak and tend to flow towards as a channel confined above or below by a stronger rock. Secondly, the rocks of the greater Himalaya are bounded by two large faults that have been active at the same time. below the Greater Himalayan rocks, the MCT, is an up to south thrust, whereas above them, the Tibetan detachment is a down to north normal fault. Third, every summer, the monsoon in the Indian monsoon dumps about 4 meters of rainfall on the southern flank of the Greater Himalaya, but less than 10% of that amount penetrates into across this decreasing rainfall gradient. Current erosion rates are diminished by 3 to 4 fold. So, for combining these observations, some geologists suggest that the intense monsoon driven erosion on the southern flank of Himalayan weakened the underlying crust and drew the partial melt channel toward the surface, thereby determining where the big faults bounding the channel are located. So, this is one model basically in which we have lot of this erosion basically above MCT, and then this partial melt of this channel basically flows towards that. So this is basically a proposed climate tectonic coupling in the Himalayan orogeny. Okay. So now we will discuss some of the geomorphic markers. So these are the geomorphic markers, basically glacier. And so what is a geomorphic marker? A linear identifiable geomorphic marker, planar or linear, that quantifies the amount of deformation change that has occurred due to geomorphic processes over the geological past. And the important parameters for a geomorphic marker, that we should know the initial undeformed geometry, and we should know the high reservation potential. Important. These are the three important parameters of a geomorphic marker. So in this case, we have this alluvial fan, like this alluvial fan or a penny plane. So these surfaces can represent as a geomorphic marker. So when we think, it has to be either planar or a linear, right? A geomorphic marker has to be planar, like a plane, or it can be a linear. And so that we know it's undeformed geometry, because after deformation, we know that that deformation happened in this. So linear geomorphic marker include naturally occurring linear features such as lavies, glacial moraines, man-made linear features like fences, lines, railroad tracks, sidewalks, etc. Planar geomorphic markers include river terraces, alluvial fans, delta marine terraces. So both these geomorphic markers are used to determine deformation or changes. So marine terraces, beaches, and shorelines, they can also they can have constructional and destructional uh, act as constructional and destructional geomorphic markers. Uh, One important thing is that the global or isostatic sea level changes within the Pleistocene are caused primarily by change in the volume of continental ice sheets. Associated swing in the sea level are huge, 120 to 150 meters. So sea level, we know the height of Chandigarh is approximately 330 meters. If the sea level rises 150 meter above, in the Bombay, so half of the India will be drowned. So you can think that 150 meter of sea level rise. You know, so these are the rises which happened in the past. The order of magnitude approximately 120 to 150 meters. So these surfaces, these marine erosional terraces, they can also act as a geomorphic marker. I think we will discuss more, river terraces actually, because we are close to the Himalayas. So I think I will quickly jump to the uh, Yeah. So this slide is also important. We can see that, there are sea level changes. A lot of these sea level changes are there, and people work on these things also. Okay. So river terrace is again, okay. The one question is whether river terrace is a planar or a linear geomorphic marker. Anybody for linear? Okay. So yes, river terrace is a planar geomorph because it's a plane. It's like a plane, right? It's a 2D plane. You can think of it as a 2D plane. So river terrace is a planar geomorphic marker. So river terraces are step-like landform that extend along the sides of a valley. And very close to, all of us know that Sukna Lake is there in Chandigarh. So if we go towards east, there is a river. The name of the river is Ghaggar River. In Ghaggar River, we have five different river terraces, right? So my question to you is, tell me whether those river terraces are formed because of erosion in the Himalaya or there is something else also, you know. So if we just go towards river Ghaggar, we can see there are five river terraces, right? Okay. So yes, we will discuss that. They form by vertical erosion of a former floodplain by river resulting in a new floodplain that abandoning the older floodplain at a higher altitude. Factors that influence the behavior of rivers: stream power, sediment load, competence of the sediment, roughness of the bed. Threshold of critical power: a river that neither aggrades or degrades is considered to be in equilibrium, and thus it is at a threshold of critical power. At this stage, stream power is just sufficient to transport the sediment load and the height of the bed remains constant. So in this figure, we can see that there are different river terraces. So T1, T2, T3, and there is, the front channel. So Schmidt will tell me what is the oldest river terrace. T1, but in geology we have always, the lower rock is the older, but here it is totally different. So this is the oldest river terrace. This is younger. This is so it's reverse. In case of a river terrace, we have the oldest river terrace on the top, and younger is down. Why is the critical power important? It indicates the potential linkage among the different variables. So just how changes in climate or tectonics would cause the river to switch from aggradation to degradation or vice versa. Okay. So now there are different types of river terraces. There are aggradational terraces, you know. So result from aggradation of the river transported alluvium along a river course, followed by downcutting, which leaves the former aggradational surface abundant as a terrace. This is a consequence of crossing of the threshold of critical power such that river moves from aggradational mode to degradational mode. So we can think of that, in the first flood, the river terrace F1 is filled, so the river deposited material up to this point. And in the second case, when the river came, it eroded its part and then it posted this. And third time this. So this is older and this is younger, this is the youngest. So this is an example of a gradation where basically river is depositing material and then again cutting it down. Degradational terraces. Now in degradational terraces, there are two types: paired river terraces and unpaired river terraces. So paired river terraces, they form where downcutting by water is greater than lateral migration of river channel, result in same elevation on either sides. Correlative terraces are preserved in both sides of the river. So in this case, we can see that T1 is present on the both side, T2 is also present. So this is an example of a paired river terrace. Uh, Unpaired river terraces, now in case of Ghaggar River, where we have five river terraces. So all these river terraces are present only on the right side of the river. But on the other bank, left bank, you don't have any river terrace. So this is the Ghaggar then represents an example of a unpaired river terraces. So they form where the lateral migration of river channel is greater than vertical down-cutting water movement. So you know the city Panchkula. Panchkula is adjacent to Chandigarh. So the Ghaggar River used to flow in Panchkula through Mansa Devi area. So it actually migrated 2-3 kilometers towards east. So because of this lateral migration, we have no river terraces, so unpaired river terraces basically in Ghaggar River. So Ghaggar River represents an example of a degradation of unpaired river terraces. Now, question is, what is the use of these river terraces in tectonic geomorphology? So three groups of processes promote river terraces. So now the question is how these river terraces are formed. A crustal movement, uplift, can be one reason for the formation of a river terrace. Second is sea level changes. I think what is happening in the frontal part of the Himalaya. I will say that sea level will not affect the formation of river terraces in the frontal part of Himalaya. I mean, uh, then climate change. So when we say climate, that means maybe we will have a lot of rainfall in the Himalaya and lot of sediments will come. Maybe that can feel like a river somewhere. So maybe next time the river is cutting those sediments. So it can be so river terrace can be purely due to climate or maybe because of tectonics or both the combination of tectonics and climate. So how can we use river terraces to calculate tectonic rates? The age of the river terrace must be known. So we need a method by which we can understand how, that what is the height of the uh, river terrace from the current river channel and what is the age of those sediments. So in order to calculate age, basically we use OSL dating, optical luminance dating, in order to understand what is the age of the river terrace. So alluvial fans, yes, alluvial fans can be used again because now alluvial fan represents a linear geomorphic marker or it's a planar geomorphic marker. Planar? Yes. So it's again a planar surface. So right. Alluvial fan again represents a planar geomorphic marker. So in Uttarakhand, we have a place where you have MBT, main boundary thrust, and it is displacing this. So we know that these sediments are deposited in, one go, but that is displacing this geomorphic marker. So if there is some kind of a displacement along a alluvial fan, then again it can be dated and it can be, shown that this is a uh, uh, tonic or active tectonics is going on in that area. We have a Logod fault, this fault where ambit is active actually. So sometimes two alluvial fans might merge, so the elevation profile might change where they are merging. And also in Pinjordon, uh, behind Shivaliks, in the Shivalik Chandigarh anticline, behind Chandigarh anticline, we have Pinjordon, and there are again these alluvial fans which are tilted because of tectonic deformation there, and there are a lot of active faults which are causing the deformation of these uh, alluvial surfaces. Lava flow, debris flow, and landslide. Despite the meter scale roughness of the upper surface of most lava flows, the surface of elongated flow can provide excellent geomorphic markers. Maybe not used here, but where you can have some volcanic activity going there, those is topographic gradients along the flow surface can be measured directly, and numerous surface features can be recognized for cross-cut correlation, cross fault correlation. Landslides, yes, landslide. If basically, what happens is that there is mass movement and all the material is deposited at once. So landslide has a advantage that you can date this. For example, this is again a debris flow. So if you just date it, you will get one precise date given the errors because this event happened instantaneously, more or less. So that advantage we have, and so the age of the deposit is closely related to we can pinpoint the age when this event happened if it can be dated. Erosional surfaces during long intervals of tectonic quiescence. Topography can be believed of by erosional processes and a low relief landscape can be produced. Isolated erosional remnants may be surrounded by piedmonts, erosional surfaces of low relief carved into bedrock. Across broader geographic regions, peneplains characterized by slightly undulating and generally featureless topography can result from long continued erosion and deposition in absence of tectonic deformation. So we can see that this area is totally peneplain. So if you go to Odisha, in India, you will see this kind of topography. All these areas are sometimes you have iron mines and other things, but more or less the topography is like this because there is no tectonic activity and it was a part of Gondwana and it separated from Antarctica. But if you go to Odisha, you will see this kind of topography there because from long time these hills are eroded and eroded. Now they have this you know shape. So when such erosional processes formed in distant geological past, they were commonly buried by subsequent deposition, such as regionally extensive unconformities preserved. So when such low relief surfaces, piedmonts, peneplains, regional unconformities are uplifted tectonically, they can form prominent markers in the landscape. So yes, sometimes these planiplanes can also be used as a marker. For example, like a lot of these, we see that these river terraces are not dated at many places. So people sometimes use elevation. They use elevation just to because they are dating one river terrace, for example, here. But at other places, they are just taking elevation and they are thinking that the age of this surface is same. They may not have just dated it, but it's just a relative dating or relative method of calculating age. So rivers and ridges crest. The course of the river and the ridge crest that are displaced across a strike slip fault can clearly record the literal offsets. In this case, we have a stream which is coming, and then there is a strike slip fault which is causing the beheaded streams. And in this case, then we can calculate what is the offset of the stream, and from that we can calculate the whether it's a strike slip fault, dextral fault, sinistral fault. So that kind of information we can calculate. So here, very close to this, we in Sathon basically we have a strike slip fault, and it is showing the same feature which as it is shown here. It is showing a right lateral movement there. So these strike slip faults, if you cut this stream, so that stream is basically displaced, and that displacement can be measured, right, to understand what is going on. And then glacial moraines. So they are linear geomorphic markers. They are remnant soil and rock left behind by moving glaciers. They have an obvious direct relation with climate change. When we consider glacial moraines a good geomorphic marker, when moraines are associated with most recent advances, although an absolute age is always preferred, an approximate age can be assigned to the undated moraines and tectonic rates. With appropriate uncertainties, can be calculated based on the observed offsets. Mostly common encountered problems with markers. What kind of problems we can face? Most typical difficulty in extracting the maximum information from a display geomorphic marker in the absence of well-documented age for the surface. We need to have an age. Knowledge of array of available dating tools, experience with the appropriate field procedures for collecting suitable material for a specific dating, and through an innovative approach of the problem of defining geomorphic ages is needed to obtain reliable age constraints and hence the deformation rates. Correlation of partial preserved geomorphic features present other challenges. As older and older markers are examined, their preservation typically becomes increasingly elementary. So preservation of, sometimes we don't have geomorphic markers everywhere. So that is again a challenge. Okay. Okay. So basically, we learned that we can have planar geomorphic markers, we can have linear geomorphic markers, and if there is any deformation in that, then we can date that and we can try to understand. So establishing the timing in the landscape, so we need some kind of dating. The science of tectonic geomorphology strongly relies on placing time controls on the landscape. Uh, until the advent of radioactive dating methods, the principal means of establishing timing in the landscape was through the use of relative dating methods. So, in this presentation, we will discuss a little bit about what is the difference between relative dating and absolute dating methods. The relative methods yield relational information only. Surface X is older than surface Y, which is in turn older than surface Z, as we do in geology. So this is a basically kind of a relative method of dating. Whereas absolute dating allows us to place a number on the age. For example, there is a terrace, river terrace, which is deposited. So X was created, let's say, 3,000 years before present. So in absolute dating, we don't need any kind of a relation with other features, you know. So that is the major difference between uh, relative dating and absolute dating methods. So absolute dating, the technique used to determine the exact age of the artifacts or a site using methods such as carbon dating. In relative dating, a technique used to determine which object or item is older in comparison to the other one. In absolute dating, we have a numerical age, and in relative dating, arrange fossils in an order. For example, paleontologists basically use fossils in order to know the age of the rock. So that is a relative method of dating. Four methods are radiometric dating, amino acid dating, dendrochronology, and thermoluminescence. And relative dating involves biostratigraphy, stratigraphy, and cross dating. And precision is high in case of absolute dating, and precision is low in case of relative dating. Quantitative measurement versus qualitative measurement. Uh, Absolute dating works better for igneous and metamorphic rocks, and relative dating works better for sedimentary rocks having layered arrangement of sediments. Expensive, so absolute dating is expensive and it takes time, and relative dating is less expensive and efficient. So this is just showing some of the absolute dating methods. Radiocarbon and C14 is used. So maximum age is around 35,000 years, which we can date, and the material used is wood or shells. And then thermoluminescence, the maximum 3,000 years, 300,000 years, and the material used is quartz or silt. Cosmogenic quartz and olivine is used 3 to 4 million years. and then paleomagnetic and biological, which is basically dendrochronology. Wood is used, it can go up to 10,000 years depending upon the existing of a local master chronology. So these are different methods. Basically, uh, in active fault or in when we study these active faults, we basically use the optical simulated luminance, that is OSL, and the material which is used is the quartz or the silt, which is present in the sand or the soil present there. So I think I will skip this part, dendrochronology. Radiocarbon dating, yes, it can be used. So naturally occurring isotope like C14 uh, to determine the age of the carbonaceous material up to 50,000 years. Maximum you can go up to 50,000 years, not beyond that. So raw uncalibrated radiocarbon ages are usually reported in uh, years before present. So this is just the natural radioactive decay of the radioactive material, and the radiocarbon clock is based on the known decay rate of unstable isotope of carbon C14, which is found when cosmic rays interact with the nitrogen in the atmosphere. The radiocarbon combines with oxygen to form a radioactive form of carbon dioxide. When a living organism dies, the carbon exchanges stops. Measuring the C14 concentration in the organic samples and provided they have not been contaminated by younger material, one can calculate the time elapsed since the material was originally formed. And illuminating basically, you know, basically we have quartz, silt, and uranium, thorium, and potassium. It is present everywhere. We have this background radiation. So you can think of that. When this uh, quartz grain is exposed to sunlight or any light, you know, then the age of that sample will become zero. But once this quartz silt is sediment, it is buried under the ground, right? It is buried somewhere. And then you have in the background, you have uranium, thorium, and potassium, and those are bombarding. So this quartz will store some of the charge. Some of the electrons will go to the higher place. So it has stored some energy. So when we go in the field, basically we can take out this sample using a pipe, and then we can bring that sample into a dark room and open that, and then do chemical processing. And then we can put it into a machine to calculate how much energy is stored in that quartz. And the other thing we need to do is we need to also understand what is the background radiation there, what is the amount of uranium, thorium, and potassium which are present in that in the surrounding of that sample. So using those techniques, we can calculate the age of that sample. That is by basically using OSL. So in this diagram, basically this is what we are showing, that there is a uh, energy stored in the sample. So there is a erosion, transport, and then deposition. Again, then it was built up, and then if it is exposed to sunlight, then it is again you have a reset basically, and then it will just tell us the last depositional event. So if a sediment is exposed to sunlight, then its age will become zero. Okay, so it's like that. So this is what it is showing. You can have thermal or optically simulated luminance. And then there is another technique nowadays. It is used as the cosmogenic surface exposure dating. It is again used to understand that if a surface is exposed, from how much time it is exposed to the atmosphere. So this is again a new technique which is used. So a constant rate of production, the number of atoms of beryllium and aluminum that accumulate in a rock surface will be proportional to the length of time the rock were exposed to cosmic ray bombardment. The amount of each nuclide would be estimated of the minimum time that the particular surface has been exposed. So if let's say there is a fault scarp or any surface which is exposed, and we want to know from how long this surface is exposed. And then in that case, this technique can be applied. It can tell you that how long this surface is exposed to the nuclear bombardment. So that is cosmogenic surface exposure ages we can get, and basically this decreases with the depth, and depth is in centimeters or inches. Okay. So I think most of the things are covered by sir. So I will just discuss the things uh, which I think are. I mean, we can discuss some of the things, and then I would like to show some of the examples of the work which we have done. Uh, can we take a break? I think here a small break. Yeah. Okay. Okay. Small break. Okay. हाँ, किस तरह? हैं? क्या कह रही मैडम? मैंने ईयरफोन बंद किया हुआ, मैं तो प्रेजेंटेशन दे रहा हूँ। आया मुझे मैसेज? क्या कह रहे हैं?